Hey guys, welcome to today's video. We'll be going over the phylogenetic tree. The phylogenetic tree is important to evolutionary biology and is a tool used to represent the divergence or the change over time in species. So this can be done either through genetic traits or physical traits. Here we have a table and a practice problem that we'll go over, but first I want to go over some key concepts for us to tackle this problem. So to our bottom we have a phylogenetic tree, and we're just going to go over certain parts of it and what they mean and why we're doing this so we can go ahead and beat that problem. So to our left we have something called an outgroup. This will be our most distant species put in this group. Also, we have some nodes here. This is where the last common ancestor was, and then what happens is it diverged into two new species. So in that middle you have the node, the common ancestor, then you had divergence into two new species here and here. And with this problem you'll see how we'll kind of tackle it, where we look for the outgroup and then we look for the species that is most different from that outgroup species. Okay, so let's go ahead and check it out. Let me just clear this up. We go back to our top and it reads, the mitochondrial ATPase proteins were sequenced for different vertebrate species. The following table shows the number of differences in amino acid sequences between each pair of species. Using the data in the above table, create a phylogenetic tree by appropriately placing each of the 5 organisms on the template phylogeny below to accurately display the evolutionary relationship between each species. So how should we tackle this? My thing that I love to say is, anytime we're looking at tables, I always look at the title first. You'll be surprised the amount of information you can get from it. So it says the number of amino acid differences in ATPase among 5 different species. So when tackling a phylogenetic tree, we have to determine, are they giving us a physical trait? Are there pictures that we can distinguish the differences between these species? Or are they giving us something more genetic, or in this case, amino acid differences? So they're giving us amino acid differences. So this is how we'll distinguish or see the different traits between these species. So let's go ahead and take a look here. So in our table, the thing that's most eye-catching is this 19 here. This is saying that D. polylepsis and E. ferris have 19 amino acid differences in ATPase. So these are far different from each other. So right off the bat we can say that E. ferris and D. polylepsis will either be here or here. They'll be most distant from each other. So what will be in the outgroup? This is the most distant species. What we can do is compare E. ferris to D. polylepsis. We already said these guys are way too different. Now we're trying to see who steals the cake for being the most different. And what we can do is we can look at E. ferris right across and tally up the amount of amino acid differences compared to D. polylepsis here. So we can say E. ferris, if we look across the board, G. gallus, A. forsteri, and E. africanus, we can say that there are 40 different amino acid differences compared to D. polylepsis, which has a whopping 49 differences. So again, we're just adding across. D. polylepsis has the most amino acid differences in ATPase. Therefore, we're going to place this guy right at the end. He's going to be in our outgroup. So we'll just write D. polylepsis. And E. ferris is going to be on the other side. D. polylepsis won the outer group prize, and we can just put E. ferris here. So now that we have our two guys on the outers, now we're going to solve for the inners. So how will we do this? So we already agreed that D. polylepsis and E. ferris have the most amino acid differences at 19. So now what we're going to do is fill our series. We said first place is the 19 amino acid differences. Now second place we can see will be this 18 number. That's what's catching my eye. At first it was the 19, now I'm jumping to the next number that catches my eye, the whopping 18 amino acid differences, and this is between Africanus and Dehydration. So now we can kind of work our way through this phylogenetic tree. So now we can easily say that E. africanus is farther away, so we can put E. africanus here. E. africanus, because D. polylepsis is far different from E. ferris, and then second place comes E. africanus at 18 different amino acids, okay, amino acid sequences. So next we look at the next number that catches our eyes. Now we have a whopping 16 here between D. polylepsis and D. gallus. So that way, now we can again work our way through the phylogenetic tree and say that G. gallus will go here. It is in third place. So as you guys see, we're working through from the most amino acid differences to the least, and we can start by having that template created, the outgroup versus the other species that's far, far away. We have these two on either side of the phylogenetic tree. Now we're working the middle. Lastly, what's the next number that pops up to us that takes the fourth place, that it has the most differences? It's this 15 right here, and I'll do it in another color for you guys. It's this 15 here, where we can compare D. polylepsis to A. forsteri, and we're saying that this is the most related to D. polylepsis, okay? So this will take our last slot here, where we can write A. forsteri, okay? And that's it. So we have our phylogenetic tree solved. Fourth place goes to the 15 amino acid differences between these two guys. And just looking at this, again, we're not given any pictures or anything, we're just given a graph. So we can say that the amino acid sequence data most likely reveals the actual evolutionary relationships among these guys, just because, again, there's no pictures involved. We're not given any type of, this species has hair. We're only given the species name, and we can see that the amino acid differences are the reasons for why D. polylepsis is in the outgroup compared to E. ferris, and how these guys all may relate to each other because of the amount of amino acid differences. For example, we can see between E. africanus and E. ferris, there's only one difference between those two. So of course they are together because of their amino acid sequence. If we look at A. forsteri and G. gallus, and it's in the way, there is just one amino acid difference. That's why these guys are together. And then of course you have D. polylepsis and E. ferris, which have a major difference in amino acid differences. Therefore they are farther out. So I hope this helped you guys. I hope you guys enjoyed the video, and I'll see you guys in the next one. All right.